Okay, let's get started. So, hello everyone. My name is Zemin Zhao. Welcome to the software vulnerability and security class. So, if you want to be a hacker, especially you want to hack binary programs, native programs, you write C program, C++ program, you want to find these vulnerabilities. You are at the right place. So this is a class about hacking binary programs. So I am an associate professor in the college, and I do all kinds of cybersecurity research, mainly at the lower levels, system software security, but I also do usable security and other things. So a little bit logistic first. So all the classes will be recorded. So right now we are recording, and I put all the videos on YouTube. You can also find my previous classes on YouTube. But you have to attend the class in person. So sometimes you have some kind of a commitment. It's okay, you email me, that's okay. So you cannot make it, that's okay. So for every class, I hope you bring your laptop because we are going to do a lot of hands-on hacking in class. I also hope you have a notebook or something so you can draw things because when you hack, sometimes you need to visualize things. You need to visualize the memory, the stack. It's much easier if you can draw things. So bring your own laptop and maybe have a notebook, but some of you may just write down everything on your laptop. So I put everything on this link. This is the link for the class. We do have cameras for this class, but I do not really use that very much. We use that to submit your homework. We use that to submit your midterm and finals. But everything else I put on this website, the lecture notes, the homework, everything, also the recordings. We do have an online CTF platform for this class. I will talk about that later. So this is a long class. We only have one session a week, 3 hours, 20 minutes. So if you want to bring food, I'm fine with that. And also we will take like one break during the class. Yeah. If you want to drink, you want to eat food, you don't need to ask me. Yeah. So a little bit about myself. Like I said, I'm an associate professor in college. I direct my own research lab. I call it Cyberspace Security and Forensics Lab, or CACTA Lab. So I lived in Phoenix for many years. So I even named my son Actors. So yeah. So my lab is called the CACTA Lab. That's my email address, website, my lab's website. So we do have an office hour before the class every week. But I will invite, I think I have already invited all of you to the Slack channel, right? If you do not get that, shoot me an email. I invite you to our Slack channel. So usually whenever you ping me on Slack, I will answer questions right away. Or if you want to have a meeting, then we can do Zoom meetings. I actually find that's more convenient because you can show me your screen and or I can show you my screen. But I do have an office hour before the class Wednesday. Also, we have a TA for the class. The TA has been developing the online CTF platforms for years. He's my PhD student. He was my master student before. Now he's PhD student. And he also has an office hour. But like I said, whenever you have questions, just ping us on Slack. But I prefer if you can just ping us on the channel so everyone else can also say your questions, right? Anyone else can chime in anytime you want. So this is a link for my office hour, but the TA actually has a different link, so I will update that later. Yeah. So like I said, I do system and software research. So if you enjoy this class, you probably is a student I'm looking for my research. So we have our team, we participate in CTFs every year. There's one particular one is called Embedded CTF. happening spring semester. Usually it's a 1 semester long hacking competition. For 1.5 months, you develop a secure system. For another 1.5 months, you hack other teams' system. We have been doing that for 6, 7 years, and usually we are top 3, top 4. If after finish this class, you think you want to learn more, maybe we can do something like that together. And also, we have a lot of research projects going on in our lab as well. So, like I said, I put all the videos on YouTube. So this is obviously public. Not only you can see the videos, everyone else online can see that. Okay, a little bit about my research lab, what we do for research and for fun. So we work on all kinds of system and software security problems, all kinds of architectures. So in this class, we focus on x86 or 32-bit or 64-bit. So most of you, your laptop will be x86, but I say most are using Mac. The new Mac is actually ARM architecture, not x86 anymore. So our research is mainly on ARM. We do Cortex-A ARM and Cortex-M ARM. So Cortex-A are those CPUs power your laptop, your iPad, your iPhone, your iWatch, those devices. Then Cortex-M are those powers very low-end devices like your Nest controller, a lot of industry control systems, and those kind of low-end IoT devices. For example, the projector there may have multiple Cortex-M CPUs inside. A car may have 10 or more Cortex-M CPU inside. We do a lot of system security research on top of those architectures. We also touch FPGA a little bit, and I believe we have to working on GPU because we are basically in the area of AI and also large language models. So it doesn't make sense for us to not work on GPU. But we just started. We also work on securities at higher levels, like machine learning security, large language models, those kind of stuff. Autonomous driving, car security. So many of those problems are actually also system and software security problems. I believe all security guys should take system and software security because that's the foundation for our security. So if you know some history about security, then I would say security started more like encryption, decryption, right? So that's the research focus before maybe 1950s. Maybe 1,000 years before that, all security is about data security, about encryption, decryption. Then in the 80s, people realized our computer systems, they can be hacked. There are all kinds of bugs we don't know. Software bugs, hardware bugs. And this class, the bugs we are studying, the vulnerabilities we are studying, people found them in the 80s. Then till now, 40 years later, they are still there, and we don't have very good solutions. We have all kinds of solutions, but we cannot really solve those problems. We also work on some formal verification, many formally verified crypto protocols, and also code, and also hacking. We participate in some CTFs. We also host the CTFs. This year, Northeastern, I'm part of the team to host a country-to-country CTF. Actually, all of you can participate. I will send you the information later. So there is a qualifying in early February, online, individual-based. Then there will be a in-person CTF during the summer. Yeah, and we will host it on campus at Northeastern. So in our lab, we do need the students at all levels for funded research, for volunteer work, independent study. So if you are interested in working with me, you can shoot me an email. And of course, you can wait after this semester. So in this class, this is not really cross-listing, but undergraduates can also register. So how many of you are undergraduates? Do we have any undergraduates this year? Not really? Okay, yeah. So all of you are graduates, master or PhD students. I have already invited you to the Slack channel. So everyone got the invite, right? Okay, cool. Okay, so the goal of this class. So this class is about binary hacking. So the title of the class is software vulnerability and security. But software is a big word. We're not really talking about all kinds of software in this class. We're not talking about PHP, JavaScript, or Java. We're talking about native software, the one you develop in C, C++, Rust, eventually compiled to machine code directly running on CPUs. So not necessarily JavaScript or Java running on virtual machines. Of course, a lot of those Java or JavaScript, they also directly running on CPUs. So in this class, we're not talking about those. We're only talking about the binary level. So the goal of this class is to provide you with good understanding of the theories, principles, techniques, and also tools used for binary software and system hacking, and also defense. So you will study in depth binary reverse engineering, different vulnerability classes, how to analyze vulnerabilities, give you C++ source code. You find the vulnerability and you learn how to exploit that. You develop exploits. You develop share code. We also learn all kinds of defensive solutions. For our research, we do more defense than attack, actually. So basically, you need to learn how to crack and protect native software. And you will get your hands dirty in this class. That's why I want all of you to have your laptop in front of you. There is no written exam in this class. Everything will be open book. The final midterm will be open book, open internet, because that's the hacking environment you should have. The only constraint I have right now is I do not want you guys to use large language models in the exams. You cannot. Let's say there is a piece of C code or a piece of binary code, and you give that to large language model and ask it to write an exploit for you. So that's forbidden for this class. However, I do not believe the large language model can do that at this point. I actually have a PhD student working on this because I want to find out if my students in this class have been cheating. So if they have been, I do not know how to do that. So we have been trying that. So with a lot of prompting, the large language model can hack maybe 1/3 of the challenges in the class so far. We believe with some more advanced training, they can hack more. But it's not something you can do in 3 hours exam. You can ask the large language model to crack every challenge in the class. So we will use x86 as example for this class, but the principles of hacking is universal. You can apply the principle you learn in the class to other architectures as well. Like I said, in our lab, our research is mainly on ARM architectures. So if you want to be a system or software security guy, so this is a map I give to after you take this class, where you will be, right? I do not really ask for any background of the students. This class is trying to be self-contained. I will cover all the background knowledge. But if you took system programming before, for example, you know how to program in Linux or Unix environment, you know what is socket, you know what is a file system, what is file descriptors, those can help you, okay? But I will cover those. If you took operating system class, that will also be very helpful. Compiler class as well. We will not go very deep in compilers, but at least you will know how the C code is translated into binary code, and why the same code, C code, will be translated into different binary code, and why they are different. So a lot of our research is actually on the operating system layer and the compiler layer. For example, Intel or ARM, they have a new instruction for security, and we think about how we can use that in new instruction, new security feature to secure applications or OS. So how do you do that? If it's OS, then you change the OS, right? You change the OS to use those new instructions. If it's application, then who will write assembly code directly right now for applications, right? No one does that. I used to play a game called Roller Coaster 2, Roller Coaster Tycoon. Yes, I still play that. I still play that on Wine, a very old version. I used to play when I was a high school student. And that game was totally written in x86 assembly. So the developer is crazy. Okay, he did that all by himself, assembly. But no one is doing that anymore, right? So if we want to protect our applications and we want to use some new hardware features, obviously we cannot rewrite everything in assembly. So what we do is we change the compiler, okay? So the application developers, they still write their C and C++ code, but they do not go to just a regular GCC. They are compiled, their code is compiled with our GCC or LLVM, which has more passes to change their code. Then new features will be instrumented in their software. So to those software developers, the security features are transparent. So this is what I teach in this class is binary hacking. You are literally hacking, sending byte to byte to those software and try to hack them, okay? Then after you take this class, sometimes I offer advanced software security class, but I'm not offering this next semester or two. I offered that before. So what we do in that class is we try to learn approaches to automatically find vulnerabilities or exploit vulnerabilities, including using large language models. Of course, using large language models is a very new thing. So before that, we already have all kinds of approaches based on logic, based on program analysis to discover and exploit. So how many of you heard about DARPA Cyber Grand Challenge? You heard about that before, okay. So that's a challenge, actually has been 10 years. Yeah, almost 10 years. So DARPA have all kinds of grand challenge. So autonomous driving is very hot right now, but I think 30 years ago, DARPA had a grand challenge to develop autonomous cars 30 years ago. Then 10 years ago, they have a CGC, DARPA Cyber Grand Challenge. And the goal of that competition is to develop automatic exploiting systems to exploit binary software. Then last year, DARPA have another challenge, which is going on right now, also brings large language model and AI to hack software. So DARPA pay the winners usually millions of dollars. Yeah, so companies, big research groups, they are competing in those competitions. So what we will do in the first week, obviously we will go through the class overview, what we're doing right now, logistics. Then we will dive into the background knowledge. So that's what we're going to do today. So we are only meeting once a week. It's actually very convenient because sometimes if I finish the lecture earlier, then we can do some hands-on exercise in the classroom. Then I can walk around to help you guys. Because this, like I said, this class is not about remembering things. It's about hacking. It's about understanding. Okay, so you have to get your hands dirty. We'll talk about those background knowledge later. So the only real prerequisite for this class is the C programming language. So I guess for those who asked me for override, I did ask you if you took no C, right? So I think most of you are qualified. It's also a good idea to read the original C book, the C programming language book, along the class. And you may find out that the classic C book, the example code in the book has bugs. Has bugs you can exploit. Yeah. Also system programming, operating system, will help you. Systems programming usually teach you how to program in Linux, all kinds of interfaces libc provides, and also Linux provides. And also some other skills you need and you will pick up in the class include reverse engineering. I will mainly use very simple tools in this class. In our platform, we only have simple tools like obj dump, but you can also use other tools like IDA-Pro. IDA-Pro has a free version. Ghidra also is free from NSA. And recently, I like to use a lot of tools called Binary Ninja. They have a cloud version. You can upload binaries there, and they can even give you decompiler to say code. The cloud version is free, so you can also use that one. Debugging, we're mainly just using GDB, not even Pound GDB. We try to install Pound GDB in our server, but there are some problems. Anyway, the most important skill for you to survive this class is the same skill you use for any research or real-world jobs. It's not about remembering. It's about good at learning, finding the information you need to find, good at Googling. It's maybe a little bit obsolete when I talk about Google because everyone now is using ChatGPT. ChatGPT is giving you, I feel most of the cases it's giving you the right answers, but not all the cases. Yeah. But self-learning, very important. Getting your hands dirty. I keep saying that, very, very important. Topics we will cover in this class, all kinds of binary attacks and defense. We're using x86. When I say x86, I'm mainly talking about the 32-bit platform. We also use a 64-bit. Actually, the server we are using is 64-bit. The OS is 64-bit, but the applications you are hacking, some of them are 32-bit, some of them are 64-bit. Sometimes it's 32-bit. It's the same most of the cases, they are the same principle, but 32-bit is just a little bit faster to hack. So sometimes for demo everything, I use 32-bit. 64-bit, sometimes the exploit is just longer, but some cases, there are different exploit, different principles. So we'll cover both. You will know how to discover vulnerabilities and also how to develop exploits. When I say exploits, I mean those more like attacking tools. And we mainly focus on memory corruption attacks in this class. But the boundary between memory corruption attacks and other micro-architectural attacks is very blurry, especially in the last 10 years. The development in micro-architectural attacks, those attacks related to cache, everything, they have been influencing memory. So the boundary is not that clear anymore. So that's why in the last, my plan is the last class we will talk about the micro-architectural attacks, like cache side channel attack. So mainly we will cover stack-based buffer overflow. Excuse me. So that's like one of the classic attack vulnerability discovered back in the 80s. We will spend several weeks on that because at the beginning, you also need to pick up all kinds of background knowledge. Then we will move faster on other topics. Actually, after you understand the stack-based buffer overflow, many other things will come much easier. Okay, even though stack-based buffer overflow may not work in real world anymore because it has been 40 years, and we developed all kinds of defense to defeat that. You will learn how to write a share code, format string vulnerability, a heap-based buffer overflow, one of the or heap-based exploitation, not necessarily just buffer overflow. So that's one of the hot topics right now. Many of the vulnerabilities we discover real world nowadays are heap-based. Then they are very hard to fix. Integer overflow, return-oriented programming. So how many of you heard about return-oriented programming before? Several, okay. But I guess most of you heard about buffer overflow, right? Yeah. So even after you learn the buffer overflow, format string vulnerability, return-oriented programming will be eye-opening for most of you. If the first time you say that, it's eye-opening. Very fun to do that. So some related papers, and also book. So there is a book I recommend. It's not required. Actually, it's a little bit more of advanced for this class. It's called Practical Binary Analysis. This one covers a lot of automated binary analysis, but in this class, we're doing everything manually, right? I believe you have to understand how everything works. That's why we're also using the most fundamental tools in this class. If you just give everything to ChatGPT, then you do not really understand anything, right? So this book has nothing to do with large language models. It has some tools the researchers developed in the last 20 years, which is a very good book, but it's a little bit more advanced for this class. A lot of what we discussed in this class were from some classic papers and also research, including my own research. There are several systemization of knowledge, SOK papers. I recommend you to read at some point of this class, not necessarily right now. One is called Eternal War in Memory, because what we do in this class is memory related. Published in IEEE Security and Privacy almost 10 years ago. So IEEE Security and Privacy is one of our top security conferences. Then after that, there's another paper, The Art of War, Offensive Techniques in Binary Analysis, talking about how to hack those. Then there's another paper on shadow stack. You don't know the meaning of shadow stack yet, but later we will study that. So there are many papers, and when I developed this class, I also inspired by those papers, adding more examples and topics there. For example, so this is the figure in that 2013 paper, and this figure basically covers everything we do in this class. Yeah, this figure talks about the attack model, demonstrating different exploit types and policies mitigating those attacks in different stage. So right now you do not understand this figure, but when we revisit this one at the end of the semester, you will realize, I mean, what we're doing is basically covered in this figure. So let's say when you want to attack something, binary code, you first need a pointer, okay? So what is a pointer? A pointer is just a variable, and that's, so the pointer, the concept here is the same concept in the C programming language. It's a variable, but the semantic of that variable is an address. It's a memory address. So that's a pointer. So it points to somewhere, right? So the concept of pointer can mean different things in different scenarios. For example, a URL, that's also a pointer. It doesn't point to a memory location. It pointed to some resources on the internet, right? So here we're basically talking about a memory address pointed to a memory location. So as an attacker, what you're trying to do is you want to make the pointer go out of bounds. You define a say array, which is 10 bytes. Then you have a pointer points to, which is supposed to point to one element of the array. But you somehow make it out of bound, pointed to other places, then there will be problems. Or you can make the pointer become diagonally. Basically, the first one is a spatial problem. The diagonally is a temporal problem. So it means you pointed to something, and that resource was there, the memory was there, the object on that memory was there, but later it was released. It's not there anymore, but the pointer is still pointing to this, right? So if you develop in HTML or JavaScript, I can give you an example. Is you have a URL on your web page. The web page points to some kind of a CSS. It's called CSS or CSS? CSS, right? Or other kind of online resources. But you didn't develop that online resource. Someone else developed that. But your page has been there for 5 years. And that CSS may not exist anymore. Then your URL in your web page becomes a dangling pointer because the resource is not there anymore, right? So then the second step, the attacker will try to use that pointer to write or free some memory resources. So you're basically overwriting something you're not supposed to overwrite. You can also use that to read something, right? Then depends on which resource data object you are writing or reading, then you can achieve different attack goals. For example, if you are overwriting the code, modify the code, then you breach the code integrity, right? If there are other pointers in the memory and you are trying to override that, then you basically breach the code pointer integrity. And all of them can be considered as data, so also data security. Then depending on what code pointer that is, the code pointer could be a return address. It could be a function pointer, right? Then you can fully control this computer. Then you may want to inject a share code to do that. And also this figure talk about how we can defeat those kind of attacks. For example, here we have one defensive technique called address space randomization. This is a technique has been deployed in our system maybe for 10, 15 years. All your phones, your laptop have this, your OS have this deployed. So in most weeks of this class, in our server, we disabled this feature to make things easier for you to hack. But for 1 week, in particular, we are going to hack this feature. Okay. So technically, we can have all the challenges on top of this feature. It will just add another layer of defense, but you should be able to hack it. There are other features I will skip today, but eventually you will see this figure covers most of what we're talking about in this class. So this is the link for our hacking platform. If you haven't registered an account, just go there and register. So right now, this is hosted in the college. So this is only available when you are on campus. So if you are off campus, you need to VPN into the campus network and access this. So when you register, please use your Northeastern email so I can know who is who. Okay, you can choose whatever username you want. I do not care about that part. So this is a platform we use for all the homework and also the midterm and final CTFs. Yeah.
Do you have access to VPN?
Everyone has access to VPN. So VPN is provided by the IT of Northeastern. Yeah. What kind of OS do you use? Apple? Yeah, Apple is easy. Just the Google Northeastern University VPN.
Okay.
You can download the VPN and everything. Yeah, if you are using Linux, it could be a little bit trouble because the VPN software. So how many of you are using Linux? Okay. It will be a little bit trouble even for me. It's a little bit trouble. So my family is still in Buffalo, so I'm commuting between Boston and Buffalo. So when I'm in Buffalo, I need to use my wife's computer, the Mac, to VPN into this. I'm trying to figure out the VPN, but it's terrible. Yeah. Yeah, let's say. Actually, we're also developing another new website. We call it the Pang IoT Academy. We are trying to bring more IoT challenges there for basically different architectures, usually mainly about ARM RISC architectures and also Cortex-M. So later you will understand it's not that easy. For example, the server we're using is Intel-based. On top of that, we have virtual machine. Then on top of that, we have Ubuntu. Then on top of that, we have all kinds of challenges, and we have containers. Every time you log in, you start one challenge. We create a container for you, So basically, the container has the Linux file system, and the system is designed that there is a flag file. It's just this, the /flag. Yeah, it's in the root directory. There is a flag file. The flag file has a secret you are trying to steal. Okay, but you cannot just can it. I will explain later why you cannot do that directly. You need to hack the battery and use that battery eventually to get the flag. But if we develop challenges for embedded systems, no-end embedded systems like Cortex-M, like those IoT devices, they do not run on top of Linux, right? There's no file system, so everything needs to be redesigned. We put the flags in a physical memory location, and we tell you what is that physical memory location, and you need to hack the firmware to get the flag. Yeah. So this is a system we have been developing, or we have been thinking about for years, but I do not really have enough manpower to develop this. It's a lot of work. Okay, so the hacking environment we're going to use, like I said, x86, also 64-bit. We do not really use Cortex-A, Cortex-M in this class, but in the background part, today, I will cover a little bit just to give you some sense how different architectures are different, so you can tell they're different. We use Linux. We actually just use Ubuntu. Some tools we use simple tools, but you can use other tools, but I do not really cover those tools in the class. I suggest you to use Battery Ninja. Ghidra you have to install by yourself. It's Java-based. It's a great tool, but Battery Ninja is good enough for most cases. In this class, I will only demonstrate using OPJDump, a very simple tool. Actually, that's good enough. If you write Python code, you can also use Plum tools. That's a Python library to make your life easier. But most of our challenges, you don't have to do that. In the class, I will just show you how to use Python 2 to that, because Python 2 is even simpler than Python 3 in this scenario. So homework. So every week there will be homework. In total, there will be 14 homeworks. But I think the last one, maybe we do not have time to do that. Then I may just give everyone 3 points for the last one. And also usually after midterm, the homework is about to redo the challenges you didn't finish in the midterm. So for those who got all the flags, then that homework you can just skip. There will be some readings. I will point you to some book chapters, white papers, blogs that will be part of the homework. Then it's mainly about hacking, debugging. Yeah. You need to submit homework every week before the class. We submit homework on Canvas. I will create a link every week. So you need to submit before the class. If your submission is late, you will get some penalty there. Obviously, because this class is open book, open internet, sometimes it's difficult to define what is cheating, right? So I encourage you guys to collaborate, but obviously you cannot just copy each other's exploit. You cannot copy each other's homework. You have to do those hacking on the platform by yourself. You need to capture the flags by yourself. In the exams, you cannot communicate with each other. You cannot post the challenge on some hacking platform and ask someone to hack for you. Okay, that's obviously not allowed. But this is not about memory, so I would say there is no reason for you to cheat. And to be honest, it's not easy to cheat in this class. It's already open book, everything. If you have DAS, if you need that, you need to let me know in the first 2 weeks so I can accommodate. The hacking homework rules. For each hacking assignment, you will submit your exploit. You will have simple write-up, several sentences, screenshots, that'll be fine. So I can, from the homework, I can tell if you understand or not, okay? That's the most important thing. I can tell if you understand. So you don't have to write very long. I do not really have time to read that very long description anyway. If you discuss with someone, mention who you worked with, yeah, you're not going to get a penalty for that. Yeah. I encourage discussion, but like I said, you cannot share your code, cannot share your exploits, write-ups, to your classmates or post them online. Okay. So for midterm and final, I always design new challenges, so you cannot find them online. But I'm running out of ideas, so yeah, so don't put them online. Okay, so there is no written exam, just a midterm CTF and final CTF. It will be the week of 8, I believe, and also the week of 14. And my TAs and my PhD students will be here to proctor the exam. I will be out of town. So how many of you know the word capture the flag already? Like the so do you know the software hacking capture flag or the traditional capture the flag? Like the traditional, right? Okay, yes. So the software one is basically there is a flag, and a flag is just a random string, and you are trying to get that string. Okay, I'll show you later. Grades. So everyone here is graduate student, so we will use this column, okay? So in total, there are 1K points, okay? 1024, 14 homeworks. So the homeworks, I would say everyone should be able to finish everything because I'm also here to help you, okay? If you finish all the homework, you almost pass the course, right? Then after that, whether you can get A or not, depending on if you can get the flags during the final exams. But as long as you finish the homework, I would say no worry about passing the class. Yeah. I will take some random attendance check, but we only have a small class, 15, 16 people. So if you show up enough, I would not really do too much about this one. Like I said, sometimes you have family commitment, you have all kinds of things. Just shoot me an email, okay? I may not give you that 1 point, but it's just 1 point, right? What doesn't matter. And I put everything online. The recording is online. There will be 2 allotments, course evaluation voters. Actually, we only have 1 course evaluation, so only 1, yeah, not 2. Integrity. So yeah, go ahead.
For the bounds on the points, is it exclusive on the upper bound? Because it said not 924 and up, and then it said 900 to 924. It's saying up to, but not including 924.
So you really care about that 1 point? Yeah, I would say above that. Yeah, yeah. It can be inclusive. It's just 1 point. Not really matter that much. Yeah, yeah. Okay, so integrity. Of course, you guys are graduate students, so you already know this. But your first assignment is to read the academic integrity policies. Some of you maybe your first semester in Northeastern, so you still need to get familiar with that. Just some examples we will skip. This one I will also skip. But if I do find out someone cheat, I will report it to the dean's office, and it will show up in your transcript, not as F, but you know, yeah, this F. This means you cheated in the class, basically. ChatGPT, like I said, in the final exams, midterm exams, you cannot use that. But for the homework, everything, if you think that's helpful, you can use it. Ethical hacking, don't attempt to break any law. If you discover real-world vulnerabilities using the knowledge you learned from this class, report that responsibly. The companies actually they will pay you. There are all kinds of bug hunting programs, bug bounty programs out there, and also Linux kernel. They pay people for hacking the Linux kernel. I have friends who make a lot of money by doing that. One of my friends who is a professor in Arizona State, and he told me that in his sabbatical semester, he was only doing hacking. He used Mac. He was hacking the Mac OS, and he wanted to prove that he can make a living by just doing hacking. And he told me that half year he made almost the same as what he was supposed to get for salary. So yeah. So you don't have to be a villain. So 10 years ago, 15 years ago is a different story. But now the ecosystem is much more mature. You find bugs, you have responsible ways to help the companies out there. Yeah. So I think that's the last slide of the class overview logistics. Any questions for this part? Yes.
So we talked about hacking,
Yeah.
and I'm trying to understand the relation between hacking and vulnerabilities.
Yes.
So when you are able to hack a system or a software,
Yeah.
so it means that it's vulnerable. So that's how you report that I was able to hack the system, so it's
Yes.
vulnerable.
Yes.
Okay.
So vulnerability, or we can call it bugs, but there are different bugs, right? Some of the bugs are functional bugs. In this class, we're mainly talking about security bugs. So then we call it a vulnerability, which means by exploiting that, you can take full control of the system. That's our goal. But sometimes the goal is different. You can exploit that vulnerability to steal something on that computer. So in this class, technically, what you need to do is to steal something in a system, which is a flag file, the content of the flag file. That's what you're trying to steal. Yeah. In real world, there are many different goals, right? And when you discover a bug, you report to them, especially when it's a security bug. Sometimes they will ask you to demonstrate you can actually exploit the bug. Because not every bug is exploitable. Some of them are too deep. We can see the code, there's a bug, but it's very hard to reach there. Yeah. Other questions? Okay, then we talk about the background, then maybe 30 minutes from now, then we can take a break.
Is today a full class or?
It's a full class. What do you mean by full class?
I mean, are we going home sooner or?
I don't know. Let's say, yeah. Yeah, I know it's very cold out there.
I had something to do. I was just asking.
Oh, I see.
Yeah.
Okay, so background knowledge, we will talk about compiler, linker, loader, talk about x86 architecture, the instruction set, a little bit about ARM. Then we will talk a lot about Linux fundamentals. Yeah. So, okay, so let's first take a look at how compiler works. So most of the developers, you develop C++ code, and the code you are writing are just text, right? They are human readable. The CPU doesn't really understand that. Then eventually, they become machine code. which is just bytes, and the CPU can understand those. So this is basically the journey of the C code eventually becomes a binary code and become a process on Linux or Unix-like systems. So first, as a developer, you develop something like a .c. Then you also write header files, right? Then if you use GCC, you can just do GCC, that's .c file, then you get the binary, right? But GCC actually have many different stages, and you can call each stage separately. Other compilers are the same. So for our research, we mostly use LLVM because develop LLVM process is much easier than developing a GCC parser. So in GCC, the part you really the first part, pre-processing, it's a tool called the CCP. You don't need to remember the name. So what that tool does is to, from your C code, it generates .i files. But those files are not necessarily stored on your file system. So when you just do a gcc.c, you do not see that .i file. But I will show you later that you can actually see that file. So that file is still a text file. It's still a C source code, but those macros has been expanded. Now after that, you can actually have the compiling stage. But the compiling of GCC is not compiling from C code to binary code directly. Instead, it compiles to assembly code. So we can use this command, GCC dash uppercase S to generate this .s file, that's assembly file. If you compile 32-bit, you can do this M is machine 32-bit. Then you get this assembly code. Assembly code is still a text file, okay? Even though everything there looks like instructions, but it's still not instructions, they are assembly file. So then we use assembly tools like AS to turn this assembly code to binary code. So what you get is .o. Right? Usually each .c file becomes one .o file, right? That .o file is the first time you get the binary code. There are instructions in this .o file. So everything before that, just text. In that .o file, you may have symbol tables, like the variable names, their address, function names, their address, different relocation entries, or where do we know the different things. Then there is a linker to link different .o files together into one program. And that program is binary, and usually that's called an executable file. But that is just a file. That's not a running program, right? That's one file on your file system. So when you actually run this program, the operating system and also some other C library programs will load your program from the file system, from your hard disk, from your other storage to the memory. Because our current computer architecture, you can only run things in memory. You cannot run things directly on hard disk. So only after that, this executable file becomes a process. So how many of you took OS class before? Okay, so in the OS class, maybe the first assignment you had was developing a shell, right? Yeah, but usually in OS class we do that, but the shell is not part of the kernel. Shell is not really part of the OS, but shell interact with the OS using all kinds of system calls, right? So when you develop a shell, you usually at least use a fork system call and the exe C system call, right? So let's say you have a program called ls. So if you use Linux, you already know ls, list the files in the current folder. But ls is a command, right? But what do you mean by command? It's actually an executable. When I type ls, means we are running the executable whose name is ls. Then you are typing that in a shell. So how does the shell node that program and eventually run that ls? So first, the shell will call the fork system call, right? After the fork system call, then we have two processes. One is the shell itself, that's the parent. Then is a new one. It's a copy of that one. It's called the child. But the child and the parent, they have the same code. That's why in the code, we need to specify what we do if we are the parent and what we do if we are the child process. So by checking the process ID, the program will be able to figure out if it's a child or it is the parent. If it's the child, then the child will make another system call, exe, save AE, or in this case, maybe exe, save AE, yeah. There are different system calls of the same family, basically, exe, say. They will load a program from the hard disk and replace the current process with the image of that program. So the current process at this moment, before you make that system call, is still a share process. Then the share process will be replaced with your ls program. As a parent, stay as a share. So that basically explains this step. Of course, it's a simplified version. There could be a lot of security features, security checks going on with this step. But that's a basic idea. So on Linux, when you try to load and execute a binary program, the OS and also the C library will do a lot of checks. There were checks or permissions, whether the user has a permission to run this program, and what kind of permission the user has, whether we have enough memories. The OS will set up a new process. After the OS get the system call fork, then inside fork, it will set up the virtual address space, everything. And also the OS will map an interpreter, also a loader, into the process virtual memory address. And in Linux, that is called the LD loader. Linux.so. SO means static library. So this interpreter will load the binary into the virtual address space. So the kernel doesn't directly do that. The kernel will load the interpreter. The interpreter is a userland program. It will load the program you are trying to run into the virtual address space. It will also pass the binary to find out what dynamic libraries this binary uses. It will also map virtual addresses using other system calls like mmap, memory map. We will see those later. Some other important steps, copy command line arguments onto the stack. This will be something related to our hacking in several weeks later. Initialize registers, stack pointers, and other registers. And after those initialization, it will jump to the entry point of the program. So usually for C programs, the entry point is _start. Okay, so this entry point is earlier than the C library entry point. So when you develop in C, what is the most important function you develop? Or what's the main function, right? But how did you get to the main function? Someone has to call your main function, right? Because you never call your main function. So C library has a function called maybe __ libc start main something. That function eventually calls your main function, right? But that __ libc start main function was called by the start, the piece of code starting from start. So the start is not necessarily a function. Yeah, you have a question?
Yeah. What does exactly loading binary into virtual address space mean?
So the binary is in your file system, right? It's in your hard disk. You need to load that into your physical memory, like RAM. But RAM is, in modern computers, we have a memory management unit to virtualize our memory. So let's say a 32-bit machine, the address space is 32-bit. So the physical memory we can have is actually 4 GB, 32-bit. But every process running on the OS believes that it has 4 GB of memory. They don't really have. That 4 GB is virtual memory. Yeah, that 4 GB virtual memory is not fully backed up with physical memory. Okay, so programs, they only say the virtual memory. So when the OS loads those to the memory, then the process can use those resources.
Right, so in the binary, we already have every piece of memory that the program needs, and then when the interpreter runs, it maps that to
We load
physical.
that.
Sorry,
So at the physical layer, hardware layer, we actually move or copy things from hard disk to RAM.
okay,
What is SO in Linux.so?
SO?
Yeah.
I think SO is static library. So basically .o is object file. Yeah, S is probably static. Okay, so next we're going to say in one example on our server to say the journey of the C program. So this is a very simple C program, but it has 3 files. We have a main file. The main file first have some macros there to include different headers. Some headers are library headers. Some headers are the ones between the less than and greater sign are library headers. Then some are just user-defined headers. Then we also have a macro there to define a usage, which is a string. Then we have the main function. The main function takes, in this case, the main function takes 2 arguments. The main function can take up to 3 or 4 arguments, I believe. Yeah. In this case, just 2. The first argument is an integer. So this is an integer, right? The name of this, well, of course, name doesn't really matter. The name here is argc. So that's just the convention we use. Say here means count, right? So how many command line arguments? This specifies how many command line arguments are there. Okay. Then the second argument is a pointer to an array. Is an array of string pointers. So actually, that is the command line argument. Command line arguments, you can have multiple, right? Then the program can access those from here. And the number can access from this. Then we have 2 local variables, A and B there, both initialized to 0, and they're local variables, so they are stored on stack. Okay, at least the compiler we are using, we store them on stack. If you are in x86, we do that, ARM, we do that. But if you are using some weird architecture, especially embedded systems, they may store them in different locations. But the C code doesn't really care about that part, right? So C code, we only know we have 2 local variables. Then we check if there are 3 command line arguments provided to this program. If not 3, then we will print out this string, then we will just return. Okay, so when you run this program, you are supposed to do AND A and B. A, B are 2 values. Okay, so you can see there are 3. When you type this in a shell, there are 3 command line arguments. The first one is AND. It's the program name itself. The second and the third are the parameters you are passing to the program. This is one way to pass parameters to a command line program, right? There are other ways, obviously. Then what you are passing here is a string, right? A, B, two values. You could put 1,000 there, you can put 20K there, right? Those are not integers. Those are strings because the parameters here, they are strings, okay? Then you need to convert those strings to integers. So there are some library functions. A to I is one of those. ASCII to integer. So after that, you really get an integer. So say this is argument 1, this is argument 2. So the very first argument is argument 0. That's the name of the program which you don't need. What you want here is A and B. After that, you get A and B assigned to the local variable A and B. Then you just print out the value. So I print out also and 50 it. So here, the printf takes a format string. Then we have AB and we call function add AB. So the function add AB is in another file. It's in another C file, so it will be compiled into a different object file, right? In this file, we only have a macro there. After that, we have a simple function and take two parameters, A and B, and just return A plus B plus 50. Then we have the header file there, right? So let's try this on our server. So this is our server. We have maybe over maybe 100 challenges there. Those are the challenges you will hack this semester. Let's say, so add. Okay, let's find the add first. Let's try 32-bit first. So if you want to play one of the challenges, just click it. Then there will a dialog like this. The practice challenge feature doesn't really work on our platform. I think you can download. Download may work. It will download the binary, yeah, for you. Most of the cases, you just click this button, run challenge. After you click this button, we will create a Docker container for you. You don't have to SSH into it. Actually, it may not work. What you do is you close this dialog, then you click the terminal here, okay? So everything you can do just in browser. You don't have to install anything for this class. So now you are in our Docker image, and if you do ls, you can see there are many things we have installed for you here. What important is, first of all, there is a flag file, okay? So first thing you notice is when you log in as the user CTF, okay? Every one of you, you log in as a user CTF. You do not log in as your own chosen username. That is for the web part, not for the Docker part. So you log in as the user CTF, but let me make this a little bit larger. But you can see this file, the flag. The owner of this flag is root, right? And you are CTF, and only root can read this file. So if you just do a cat here, if you just do cat flag, it's permission denied, okay? You will not be able to get the content. So then this is the binary you are going to use in this class. It's always highlighted like this. For this one, you're not going to get for this challenge, you're not going to get the flag. For other challenges, your job is to hack this binary and eventually use this binary as a springboard to get the flag. Okay. So after you get the flag, you can submit that in any challenge here. Okay. You can submit the flag here. Okay. If it's correct, it will show, for example, this one. 4 people solved that. So each of you have a different flag. So if you just get a flag from somewhere else, we will be able to catch you. Yeah. Okay, go back to our terminal here. For this one, we actually have a code here. So there is a code folder. So we put everything, for this challenge, we put everything in the code folder. You can say, and. Okay, so you can see we have the main.c. We don't need this one. I'm not sure why this one is here. Then main.c. So if we do a GCC main, the reason we cannot do this is the output. We don't have permission here. So let me just output to a different location. Output to temp a.out. This will work. Yeah. Undefined reference to add. I think we should do GCC and add.c like this. Okay. So when we compare this, use one command of GCC, we will generate one a.out. I put that in a temp folder, temp a.out. Okay. So this is what we just compared, right? So when we do this, if we do some numbers, it will just add those numbers together. Of course, this program itself has bugs. That's why you see some weird numbers. So there's overflow basically, right? But this is how it works when you compare a program. But if you use, let's say, this command to compile, so when you compare this, you only get one a.out. But if you use a different command, let's say we use this, I'm not sure if we cannot do it here. We still need to do it at let's see if the temp files will be. Oh, the temp files will not be saved there. How do we save temp files to other places? So the problem right now is creating this add.i file and main.i file, as I explained to you before. The .i file, but it has to write the .i file to the file system. But right now we don't have permission to do that. Okay, we can copy the whole thing to a different place. Let's say we copy, we make dir add, then we just copy the whole thing. Code. Okay, after we copy everything there, then we will be able to compile everything in the temp folder. Oh, it's actually here. Now we try to compile this program using this command. So this command is different from the previous GCC. Previously, we didn't specify any options. Now we have option is, so this dash WO means we want to show all warnings. Not very important. The important is this one for this challenge. We have save temps. It will save all the intermediate files to the file system so we can inspect them. Okay. Without this, you will only get the final one. So here we're going to compile this into a 32-bit program, optimization 202, and we have those two files. So when we do this, so now you can see we only have those files here, right? So after we compile this, we can get many other files. We got the .i files, .o files, .s files. So let's take a look at the .i file. So this is a .i file. It's a little bit different from before. So if you compare with the .c file. So say in .c file, the first line is include. It's a C directive, right? Now we don't have this anymore. We are actually including what is in this .h file here, right? The .h file actually only has this line. If we can't add .h, you say it actually only have this line. So this line is copied into this .i file, and that macro, the base is a macro here, that doesn't exist anymore. That is expanded to the actual value of that. But this is still readable. It's still a C code. But if you look at the main.i file, it may be much more complicated because the main.i file, there are many different include many libraries. So we have many different things in the file. The file is getting much larger, right? Much larger. So that is basically how this compiler works. Any questions so far?
You said about fire systems?
Yes.
What?
File system, so you have hard disk, right? You cannot store files directly on the file disk. You have some layers of abstraction for the OS, for the applications to use. And that is a software system we call file system. Yeah, so file system will provide all kinds of interfaces. So when we do ALS there, we can say in this file system, in this current directory, what files we have. So next we talk about the x86 architecture, or maybe let's take 5. Yeah, we come back in 5 minutes. We come back in 2025, 7:25.
The last 20 minutes of the class.
No, I'm not sure.
The last 20 minutes of the class.
What do you mean?
Are you gonna be alone for them? I'm Miriam.
One of the other day, I was wondering what I.
You can leave early, yeah. It's hard to tell. If you have to. Yes.
Nice to meet
everything-
you.
And for the next time, so imagine they have something to do, can we go in class through Zoom?
Yes, yeah. If you cannot make it in person, yes, you can do that.
The link is very jump.
I didn't provide that link anywhere, but if someone needs that, I will just send to your house. Yeah. But I prefer
Yeah, me too, I think
show up in person.
just
Yeah.
in case.
Sure.
Command that we use, what is the purpose of the hyphen E?
Oh, we
Oh.
don't, okay.
Don't remember. It's basically a pre-processing. Yeah. Will prevent some insertion of some directives. Okay, everyone is back. So we move on to the x86. So before that, several data types. 1 byte is 8 bits. Usually when we say a word, it's 2 bytes. D word could be 4 bytes. Forward, that's 8 bytes. So for this architecture, then endianness. So both Intel and ARM and most of the architectures we use right now use little endian. Basically, that means the least significant byte is stored at the lowest address. Let's say we're trying to store something at the address 0. Okay. And what we are trying to store has 4 bytes. The value is 7856. 34 and 12. That's the value I'm trying to store in hex, right? So that's fine. That's 4 bytes. And the most significant byte here is 78 in hex. And in little endian machines, it means we're going to store them at the highest address. We're storing at the address starting from 0, which means the highest address is address 3. Okay. So we're storing 78 at 3, 56 at 2. Okay. So that's little endian. We do have some big endian machines, and those machines store the least significant byte at the highest address. And this works for different data types, keyword, forward. But if you have a string, it doesn't really matter, because a string is just an array of characters. Okay. There is no endianness. It's just based on the appearance of the letters. For this architecture, there are several base registers. There are 8 general purpose registers, 1 flag register called E flags. So the older version, the 16-bit version, may be called the flags. The 32-bit version is called extended E flags. Then there is a instruction pointer register. So pointer register means it stores the memory address. Okay, it points to the next instruction to be executed. That's called the IP instruction. Because it's 32-bit, it's EIP. There are some other special purpose registers. So those are the general purpose registers, 8 of them, and they are easy to remember. First, we have A, B, C, D, AX, BX, CX, or EAX, EBX, ECX. At circuit level, they may be a little bit different. For example, if you want to use a counter, usually you use the register ECX. Circuit level, it may be optimized for that. When you want to do addition something, you probably want to use EAX, but that's more for older CPUs. Now they are all very fast. So EAX is a 4-byte register. So the lower 2 bytes is called AX. That's compatible with the older version of the CPU. Go ahead.
Does the instruction pointer register on the previous slide, does that serve the same purpose as a program counter? Or-
Yes, that's a program counter. Yeah. In some other architectures, that register is directly called program counter. In Intel, it's called IP. Yeah. So the lowest 1 byte, it can be directly accessed, called AL, BL, CL, low there. Then the higher one could be AH, BH, but those are very historical. We don't really directly use those registers directly anymore because the data we're processing is much larger right now. Yeah. Then we have 4 other general purpose registers: ESI, EDI, ESP, and EBP. ESI, you can remember this as source index. Okay, so you can store whatever source is. DI is destination index. SP is a stack pointer. BP is a base pointer, also what we use on stack. So those are the registers very important for the buffer stack-based buffer overflow. So those are the 8 general purpose registers. The flag register or the E-flags register has many different bits to indicate the computation status. For example, there is a carry flag, parity flag, 0 flag, sign flag. You probably already learned this in the assembly language class or computer architecture organization class. Yeah, so EIP is a program counter. So this one holds the memory address of the next instruction to be executed. So the key here is memory location because the instructions, the code are loaded into the memory. Okay, they're not in hard disk, they're not in registers, they're loaded in memory. There are many other registers in the 64-bit version. So this figure shows most of the registers. Let's say we are already familiar with EAX, EBX, ECX, EDX, general registers. There are several others: EBP, ESI, ESP, EDI, right? So that's 32-bit, okay, started with E, extended. Then in 64-bit, those registers are getting bigger. Now we have 64-bit registers, RAX, RBX, RCX, those are 64-bit, okay? The lower 4 bytes is still called the EAX, okay? So compatible with the older CPUs, but they're bigger. Not only those registers are getting bigger, we're getting more general purpose registers in the 64-bit machine. So you can say here, we have R8, R9, R10 to R15. Those registers didn't exist for older machines. Okay. The EIP also becomes RIP because they are 64-bit.
So when we talk about 64-bit architecture, you said it'll be RAX, RBX, RCX.
Yes.
So there's a difference of space. I mean, there's more space in the register.
Yes. So those registers are 8 bytes, 64 bits.
So, like, what does it actually store? Like,
It can store anything.
anything.
It doesn't really matter. Well, this is what the hardware, the CPU provides.
Okay.
How you use that depends on software compiler decide that. So you can also find some other control registers. So on this side, you can see some control registers or configuration registers. We're not really using those registers in this class, but if you are taking a OS class or you are taking a OS hacking class, then you're going to use some of those registers. For example, say R3, this register holds the memory table locate address, the physical address of memory tables. Because memory tables is what MMU use to translate virtual address into physical address. But that's a lot of information. You cannot store it in other places, but you have to store them in memory. Then where do you store? That is held in this particular register. If you design an OS, you have to use this register. Different architectures will also have a register like this, of course, different names. For example, on ARM, there is a register called TTBR, I believe. It's called Translation Base Address. So that's basically the address for memory tables. Then you can say here we have some debugging registers for debugging purposes. Here we have some system registers. We're not going to use those. We will touch those old registers, CS, SS, a little bit. Then this side, we have some multimedia registers. You can see they are much bigger. Some of the registers can be 512 bits compared to the general registers we have here. They are much bigger. But in this class, we are mainly use registers, those registers, and the flag, and also, many this one. Okay. Yeah.
How can a CPU that's 64 bits use a 512-bit register, because it cannot, right?
So when we say 64 bits, we're talking about most of the registers are 64 bits. There are other registers are bigger than that. So those parts actually, they're more like a multimedia. They're kind of like the registers we use in GPUs.
But can the CPU address like locate those in the address space?
So those are registers, they are storage.
Oh, okay.
Yeah, they're not in memory. All of this, they are part of the CPU. They're made by usually SRAM. Yeah.
Okay.
Yeah, so memory is usually DRAM. Yeah. So all of this, they are not addressed by an address. They are addressed by the name of it. Yeah. So the instruction is like move EAX, not move address. Instructions. So in this architecture, the instruction has several parts. There can be a label if you are writing assembly code. Then there is this melodic part. This is the name of this instruction. Then there can be several operand, several. Some instructions do not have an operand. The operand is more like the parameter for that instruction. Right? Some of them have up to 3. So the operand can be a number, which in this case we call immediate value. It can be a register. It can also be a memory location, memory address. We are going to use the Intel syntax in this class. So some of you probably know that there were 2 different syntax at the assembly level, which were popular in the last 30 years. One is Intel, another one is AT&T. It's a little bit strange because Intel developed the CPU, but somehow the AT&T syntax get very popular. But in this class, we use Intel syntax because it's much more consistent with the syntax of other architecture. For example, if you do ARM, there is no 2 syntax. There's just ARM syntax. In the Intel syntax or ARM syntax, the first operand is the destination. Okay? In the AT&T syntax, the last operand is the destination. Yeah. Let's say one example, the halt instruction, it will stop the CPU. So this instruction doesn't take any argument, right? So there's no operand, just the halt, that's it. Then there's another instruction, increment, INC. It will increase the value at a register or memory location. So you need to specify what you want to increase by what, right? So either a register or memory location. Then add instruction, this add has nothing to do with the save function we developed before. So this is a entire instruction. This instruction takes two operands. It will add the register value, two register value together. Then remember, the first operand is also the destination. So we're going to store the result back in the first register. Okay. Then we have signed multiply. Yeah, then we can have this is the destination register. We multiply this one register with a constant or another register and store in here. Okay. So that's different instructions with different numbers of operands. We can skip this part. So how do we address memory? We use at the assembly code level, we use the square bracket to represent memory locations. Let's say the instruction is move bracket EAX, then bracket EBX. The first operand is the destination, okay? And because we say the bracket here, it means this operand specifies a memory location, not a register. And that memory location, the address is in the register EAX, okay? So we're moving, so basically this instruction, we are moving or copying, not really moving, right? Because we're not going to change the value in EBX. We're copying 4 bytes from the register EBX into the memory location, okay? And the memory address is in EAX. We're not moving the value in EBX to the register EAX. We're moving to memory, okay? Because this is bracket. So the second instruction, ESI -4, then we have bracket there. Then the first operand is EAX. So the second operand has bracket, that's memory. The first operand is just a register. So we're moving from memory to CPU register. Well, the memory address is ESI -4. That's the memory location. Then we're moving that 4 bytes to the register EAX. The third instruction, we can do a more complicated calculation here. So here, so what is CL? Do you guys still remember? CL is part of ECX. The least significant byte of the register ECX is called CL. So back in the 70s, if you have a 8080 or 8086 CPU, they only have CL. It's 8-bit CPU, right? They only have AL, BL, CL. Okay. So CL is only 1 byte, right? So this is a register, and this part is memory. So we're only moving 1 byte. We're not moving 4 bytes anymore. We're moving 1 byte from this register, copying 1 byte from this register to a memory location. And that memory address is at ESI plus EAX times 1. Okay. So obviously you can have another register, different numbers. So you can say if you want to try to move something to an array, then you can specify the size of the elements of the array here. In this case, maybe the size of element is 1. If it's 4, then you times 4. Then you can have a loop to write this. So this one is similar. The second parameter here is bracket. So this is a memory location. The first one is a register, EDX. So we're moving from the memory location ESI plus EBX times 4 move this value into the register EDX. Okay. Any questions so far? Good. Okay. Sometimes some instructions can be a little bit confusing or ambiguous. Let's say this instruction. Move the intermediate value to a memory location EBX. So what can be confusing here? So the number 2 can be presented with 1 byte, right? It can also be presented with 4 bytes. And we're only specify the memory location EBX. It's actually a starting address, right? So this instruction is ambiguous because we don't know how many bytes we're actually moving. The CPU doesn't know that. So this is not really a valid instruction, okay? A valid instruction looks like something like this, okay? The other 3. If we're only moving 1 byte to that memory location starting at EBX, then we will have a byte pointer here in this syntax. Byte pointer. We're telling the CPU we're only moving 1 byte. If we're moving 2 bytes, there will be a word pointer. So there's a D word pointer, then you know we're actually moving 4 bytes. So if you disassemble code, you say something like this, yeah, don't be surprised. But if you say something you don't understand, Google or ask ChatGPT what it means. So this is data movement instructions. You can move from register to register, memory to register, register to memory, and also just some value to memory or the next very important data movement instruction is the push and pop instructions. We will try to briefly talk about this, but next week we will revisit this because this is directly related to our hacking. So the push instruction will push some value onto the stack. Okay. Then what specifies where is the stack? The push instruction doesn't specify that. There is a register called ESP. That register specifies the top of the stack. So basically what this instruction does is it will first decrements that ESP register by 4, then place the operand in that instruction to where ESP points to. So ESP always points to the value in this case, right? So we can push a register, we can push a memory location, we can also push some constant value. For example, if we push EAX, then the value of EAX will be stored on the stack and the ESP will move down. The opposite operation of push is pop. Pop will just pop whatever from the stack to a register. It can actually pop to a memory location as well. Let's say pop EDI, then we'll pop the top element of the stack. We're pop whatever ESP points to, move that or copy that into EDI. Then move up ESP 4 bytes in this architecture. Okay. So both pop and push do not we're implicitly look for the stack where ESP points to. So it's related to the ESP register. Another related register instruction is called load effective address. The name here is a little bit confusing. You can remember this. We use this instruction for quick calculation. So for example, this instruction, the second argument, the operand is the memory location, right? Because the bracket, memory location. Then the first instruction in this case is a register. So we're not really moving any value from the memory to this register. Okay, what we are doing basically is to this calculation EBX plus 4 times ESI, move the result of this, not the memory of this, and this the address, just the result of this to the register EDI. So it's actually for a quick calculation. Yeah, so historical reasons, this instruction is a little bit weird. But we are not going to say many of this. Go ahead.
Why is there an 8 instead of the 4 for the quantity?
Oh, this is a typo, yeah. Sorry about that, that's a typo.
Does this syntax use parentheses ever, or does it just know the order of operations for multiplication? Or like, would it recognize parentheses if we tried to do something like that when it calculates multiplication like that?
It were not access the memory. What's your question again? If
So
you don't have the
when it has,
brackets,
like +4 times like the ESI value, that if we wanted to have parentheses around the EBX +4, for example, would that be valid syntax?
EBX plus 4.
Yeah, like it,
Yeah, we don't have an instruction to do that. Yeah, if you want to do something like that, you lead the 2 instructions. Yeah, we don't even have an instruction to do like EBX plus 4 times ESI to move to another one. That's why this instruction serves that purpose. Yeah. So if you, for example, if you want to do this, technically you can do an instruction of multiply first of this part, then do an instruction of addition this part. Yeah, that takes 2 instructions. Yeah, that's why this is for quick calculation. There are many arithmetic and logic instructions, and subtract, decrements, integer or sign multiply, shift, shift left, shift right. If you do a lot of reverse engineering, like if you're in your CTF, you do a lot of crypto challenges, you may say all those instructions a lot. But for this class, we're not going to say shift a lot. But I still want you to know those that. So when you say that, you will not be surprised. Then control flow instructions. So when you have a piece of program, when you have a piece of instructions, they will be executed one by one, right? One after another. Unless there are control flow instructions, then the control flow will not go to the next instruction instead of others. So one of the control flow instruction is just a jump instruction. At the assembly code level, you can jump to a label. You can also jump to a register. So you can see the difference between those two. If you jump to a label, at machine code level, there's no such thing as label. The label eventually becomes an address. So then you are jumping to an address. So hard coded at the instruction, jump to an address. So that is called a direct jump. Okay. If it's a call instruction, that's called a direct call. Then you can say other type is jump. Then the parameter here is a register. Then if you just read this code, after you compile this code, you don't know the value of that register. You only know that value of register when you reach that instruction, right? So those are called the indirect jumps. So there are security implications of those. Then there are conditional jumps. So those are, yeah.
Give an example of the indirect jump.
Direct jump?
Indirect jump.
Indirect jump, I mean, just jump to any location.
What would be the purpose?
Let's say you have a if statement, right? So after you compare that, then usually you will use a conditional jump there. Yeah, based on the predicate, you decide to jump to here or a lower address. Yeah. Then there are conditional jumps. They're also easy to remember. Like I said, there are different flags before, right? There are 0 flags, equal flags, something like that. Then jump equal means when the equal flag, the bit is set, then you are going to take the jump. Or jump not equal, jump 0, jump greater or equal, jump less or less or equal. So you don't need to remember this when you say those instructions. If you do not know what that is, just Google, like I said. For example, here, we compare two instructions to compare two registers, EBX and EAX. We compare which one is bigger. So then we jump less or equal. If it's less or equal, we're going to take this jump. Otherwise, we just force through. Then kill the next instruction. The compare instruction the purpose of compare instruction is to set the E flags in registers. So we compare the value of something, then later, based on that, we can make control flow decisions. Yeah.
Is it comparing, like, which is the greater and which is the lesser?
I think it's the first one. It were
Okay.
minus the second one, subtract the second one from the first one. Call instructions. Those are used for making subroutine or function calls. In say, in previous example, we have a main function, we have an add, we have a main function, we have an add function. The main function calls the add function, right? So when it is compiled, the main function will use the call instruction to call the add function. So this instruction can call a memory address. So the main add, it will actually call a memory address, the address of the add function. It can call a label and assembly level. It can also call a register. So when you call a register, it's an indirect call. So only when you execute that, you know what is the destination. So this instruction does two things, okay? So this is the easiest way to remember this instruction is two things. It first pushes the next instruction's address to the stack. So we have a call instruction. After the call, there will be other instructions, right? The next instruction has an address. We will push the next instruction's address onto the stack. So it's a push. So it will use ESP. Okay. After that, it will make an unconditional jump to the code location indicated by the operand. Okay, 2 steps. So why we are doing the first step? Why are we pushing the next instruction's address to the stack? Yeah.
So you know where to return to?
Exactly. So that's basically we are saving our. So when we make a call, eventually the call will come back, right? So we need to save where we come back. Then we just basically jump to the destination. The opposite operation of call is return. Okay? So there is a return instruction. Other architectures also have call and return. They may have different names. They may look a little bit different, but the principle is the same. So the return instruction is the opposite operation. So basically, it has a very simple job. It will pop whatever the ESP points to EIP. EIP is a program counter. So ESP points to is supposed to have at this point to what is the call pushed there. That's a return address. So we're popping that return address back to the program counter. So our buffer overflow attack will exploit this. Because we're going to pop something from the memory to the register, and memory is not safe. We can overwrite memory. Yeah, question there.
On the call slide, what were the three syntax, or the three usages? It says call label, call register, and then call mem.
Yeah, memory address.
How is that different from label?
So label can only exist at assembly language level.
Is it the virtual address?
It's no, it's like, let's say you have a label for that function, right? This is the main function, or you have a label for a memory location. You just give it a name. But that's not really an address. At an assembly code level, program level, they don't care about the actual address. Eventually that will be compiled into an address, right? So when I say label, I mean the assembly node level. But at the memory level, it's just address, numbers. Yeah, you can directly use the numbers. So when we disassemble code, so a lot of what we're doing in this class is to reverse engineer the binaries. When we reverse engineer the binary, we don't really get labels. Yeah, unless the compiler, what's that called? Disassembler is very smart and try to make it easier to understand. It will create labels. But if you only look at the machine code, there's no labels. So the stack. A stack is a very important data structure or very important mechanism, right? So it supports procedure calls and also passing of parameters between those procedures. Procedure here is basically means function. So stack is located in memory. It grows towards lower memory. Okay, so the Intel ARM, they grow towards the low memory because when you push something, the ESP value is -4. Yeah, so it grows to a lower memory. So if we pop something, the value actually increments. So there are two more instructions about stack, but we can skip them for now. So there is an enter instruction equivalent to those three, and the leave instruction equivalent to those two. But we will study them maybe next week. Guys, I think I have to take this call. Can we take like maybe 5 minutes break? My wife is calling me multiple times, maybe something emergency. So yeah, let's get back in 5 minutes. Sorry about that. My wife doesn't know how to charge Tesla. Crazy. Well, it's some kind of emergency actually, and she still has like 23%. So that's under and leave. We will talk about those next week. Okay, 64-bit architecture. We already talked about this a little bit actually. So you can see the registers are getting bigger, and we have more registers. This is another example to show you that why the same piece of C code, when they compare to 32-bit or 64-bit, 64-bit will be much faster. Let's say we have a main function lang a there. So lang means 8 bytes, 64 bits. So this program can still run on a 32-bit machine, right? But in 32-bit machine, we don't have a register that big, right? which means we need two 32-bit registers to hold the value of A there, okay? So A in this case first, it was at, it could be on stack, it also could be on register, depends on the optimization levels. The program will print out the size of lang for different architectures. Then convert that value from the string to integer, then add them together. So then we're going to say two versions of the same code on the server. This is the 32-bit version. We're going to use the tool objdump to get the assembly code of this. So the command is -d means disassemble. Then the program name, in this case, it's where's the program? Yeah. So when you do this, you get the instructions of this program. And you can say here, this is the, let's use the Intel syntax instead of, to use Intel syntax, you do -m Intel. Now you get the Intel syntax. Okay. So you can say this function has 7 instructions. We're looking at the add function, not the main function. The main function, where is it? This is the main function. It's kind of big. So the add instruction, the add function has those 7 instructions. The first instruction is called UNDBR32. That's actually a security feature. That's a security feature only came out recently, maybe in the last 5 years. It's related to control flow integrity. When we talk about that, maybe in the middle of this semester. Today we are going to focus on the other instructions. So you can see we are moving the values to the register EAX, EDX. Then we are adding them together. We are using 2 add instructions. There is one add, ADD. There is another one, ADC. So that same is carry. Add with carry. Okay. So you add the 2 32-bit value together. Then you get 1 bit of carry, right? Then you add another higher 2 32-bit together and also that carry. Then you get an addition of 64-bit value with 32-bit registers. Seven instructions here. The same C code we go to 64-bit. We do objdump. The white space has some problems. -d -m Intel. In this, we look for the same function add. You can say we only have 4 instructions. Actually, the first instruction is still that security feature. The last instruction above is not an instruction anymore because the function already returned actually. So the decompiler, the disassembler has some errors. They think that's an instruction, but it's not. So actually, we only use 2 instructions to do the calculation in this case, instead of 6 instructions before. Right, because the registers are already 64 bits. Okay, so this is a comparison of those, and those are the instructions you can use to get those. just give you a quick feeling of what other architectures look like. So for most of your phones, and even the new Mac laptop, you're using Cortex-A architecture. And the registers are different. First of all, there are more general purpose registers from X0 to X30. That's 31 general purpose registers. In Intel, we don't have so many general purpose registers, even new ones, 16 something. Here we have 30. Then those are special registers for different levels, and obviously they have different names. The instruction set are also different. So this is for Cortex-A, your laptop, your phone, your iPad use this CPU. Then for Cortex-M, it's a much simpler architecture. It only has like 12 or 16 general purpose registers, and each of them is 32 bits. Okay, Linux file permissions. In the Linux system, each file and the directories have 3 user-based permission groups: owner, group, and others. Right? Owner is the owner of the file. By default, whoever created this file is the owner, but you can change owners. The group can contain multiple users. Everyone else, not user, not group, belongs to the others group. Then for each file, for each user type, there are 3 permissions: read, write, and execute. This is a screenshot from my old laptop. We do a ls in this my home directory. Then we can see so many files, and the very first columns are the permissions. Okay, so there are 3 users, and each one has 3 permission types. That's 9 columns, right? Then there is one more column at the very beginning that specifies the type of this file. For example, if it's just a dash, then it's just a regular file. If it's D, it means this is a directory. Okay. So the first one column is the file type. Then we have the permission groups for owner, groups, and others. There are 9 columns. The first 3 for owner, middle 3 for group, last 3 for others. Then we have this is the link count, not important for today. Then we have the user for this file, owner for this file, and the group for this file. So I don't really have any groups there. That's why the group is the same as the owner. Then we have file size. Last time this is modified, and the filing. Yeah. A very important concept for this class. It will help you understand how our online CTF system is designed. Is set UID programs. So when a program is loaded into the memory to become a process, the Linux system will associate different user IDs with that process, and also group IDs. Then there are 3 user IDs in Linux. The first one is called the real UID, the real user ID. Then we have the effective user ID and the saved UID. What is important for this class is more like the real ID and the effective UID. So the real UID for a process is basically the UID of the user ID of whoever or process, because not only users can create a process can also create a process. Whoever created this process, a process real ID is the ID of whoever created that process. Okay, then effective UID. Most cases, the effective UID is the same as the real UID, except for something called the set UID programs. So that's we are going to talk about the set UID. For set UID programs, so they are programs, so they are in the file system. you can make those files, the programs in the file system as set UID programs. There are commands to do that. If that program is marked as a set UID program, when this program is executed, the effective UID, so the effective UID is not the real UID. Real UID is whoever is running this. If this is a set UID program, the effective UID is the owner of this program. Okay, not whoever runs this. So why? There are some programs in the system that are set UID programs. So the last bit here, you can say most programs, if it's runnable, it will be a X, means this is executable, you can run this. But if it's a set UID program, it's not X, it's S, okay? Which means, look at this program. This program, the owner is root, okay? This is on my program, on my Ubuntu. I log in as a user, Zeming there. But the owner of this program is root. So when I run that program, the effective UID of that program will be root, will not be Zeming. But if other programs, let's say touch, this program is not a set UID program. So when I run this program, the effective UID will be Zeming, will not be root. Okay. And Zeming and root have different permissions in the system. So that's why this is important. So this is one example. We have a read secret program here. There's a main function. This is a main function. We are going to set this program as a set UID program, okay? The program will first get the UID. When this program runs, it will first get who is the real UID. So since we log in as the user CTF on our platform, so this get UID should get the user CTF. Then we're going to call the system call get EUID. Because this is a set UID program, when we do get EUID, we're getting the user, the owner's UID. The owner we will set as root. Okay. Then we will print out the flag. So there is a function called print flag. Basically, the print flag function is this, very simple. It will open the flag file, read that into a buffer, then just print it out. Okay. So we saw that before we do a cat flag, we cannot cat the flag, right? Because we are the user CTF, we don't have the permission to do that. But when we do it here, when we make this function call or system call, open that file, it will check whether we have the permission. But in this case, we have the permission of the owner because this is a set UID program. So we will be able to print the flag. Okay. So yeah.
Where in there did you make it a set UID program?
So in the command line, there are commands to do that. I don't remember. I think you can just do that with change mode.
Okay,
Yeah.
okay.
Yeah, change mode, because change mode change all the permissions. Yeah, I think change mode plus S will do
Oh,
that,
yes,
yeah.
okay.
So here we go to the challenge. Read secret, 32-bit, 64-bit, doesn't really matter. Okay, so when we run this program, you can say the first line output the real ID of this program. Because we are running as CTF, we can never log in the system as root. So our UID there is CTF. The UID number is actually 1000. However, because this is a set UID program, let me prove to you that this is a set UID program. So you can say there is S here, right? So this is a set UID program. And because it's a set UID program, the effective user ID is actually root, okay? It's not CTF. And because of that, the program is able to print out, read the flag and print it out. Yeah, if you, so let's say, we have, so we have the cat, right? So cat is not a set UID program. So when we run cat, we will run as a user CTF. So we do a cat here. We do cat. You will not be able to cat the flag. So all the challenges in this class will be marked as a set UID program. That's why when you exploit that program, you will be able to steer the flag. So that's how we design those challenges. The ELF files, so executables, linkable format, that's called the ELF files, that's used in Linux systems. Different from Windows systems, the extension name on Linux or Unix-like systems doesn't really matter that much. On Windows, the extension name is very important. It's associated with how you run this program, how you open that file. In Linux, not really. So for ELF files, there are many different extension names. There could just be something like a bin binary, .lf, object file.o, kernel modules, ko, static library SO, or .a, SO may be a dynamic library. .a is a static library, I believe. Yeah. Also, AXF, usually for embedded systems. So this file type contains the program and code. Program and data. The program is basically code, right? You can use file to, so there's a command called file, can tell you what file it is. It's not super smart, it's based on the magical numbers at the beginning. So let's say we do a file on the bin ls, then you can say this is a L file, 64 bits. This is stripped. There is no symbol information there, and this is dynamic linked, and it uses noder of this one. Okay, so you can use file to do that. There are many different sections in a headers in a ELF file. We can use tools like readelf to do this. If you read elf -a there, you can get the headers. So this is what the header looks like. And the header tells what type this system is, what CPU it can run, and what kind of section headers are there. Yeah. So some sections you will get familiar include the .text section. .text basically is that code. That section has the instructions. .plt, .got, that's something we will learn in several weeks. These are for dynamic libraries. .data section for global variables. .data section. .ro data section for read-only data. Okay. .bss for uninitialized global data. So in C programming language, if you have a global variable and it's not initialized, then the C standard requires the program to initialize that to 0. So those ones will go to the BSS section. So for example, you have some global variable like A, B, C, D, and they have different numbers. They are initialized. Then that ELF file has to remember those, the memory locations of those variables and also the value you want to initialize, right? So when the loader copy your program from hard disk to memory, it will also copy those values, right? But if for uninitialized values, you didn't initialize that, and the C standard tells us they should be initialized to 0. So the loader doesn't need to copy anything. The loader will only reserve the space, then do a memory set to 0. That's it. And also in the L file, there is no values for those variables because they're not initialized. Tools for L files, use GCC to compile. You use readelf to pass the header. You already see that obj dump, object dump to get the disassembly code. NM to build the symbols. You can actually also change those files, use patch or obj copy. We're going to use those tools a little bit in the share code development class. Yeah. You can use strip to remove the symbols. Obviously, all of those, there are libraries for you to program as well. Memory map of Linux process. This is also a topic that constantly changing, but something we're talking about here is historical. When we talk about address-based layout randomization, you realize things has been changed. So basically, each process in this system, they have their own virtual memory. That's basically what you asked before, right? For 64-bit machine, the virtual memory is bigger, but not full 64-bit. Okay, so the computer we're using, I think right now we're using maybe 39 bits for address or 49 bits. 39, I think. No, 49. For 32-bit machine, we're using full 32-bit. That's still very small. That's only 4 GB. But for 64-bit machine, we're not using full 64-bit for the address because we don't have that much memory right now anyway. Yeah. I think it's 39 bits. Yeah. So if it's 32-bit, then it's basically 4 GB. And those virtual addresses, they are mapped to physical memories by page tables. And the CPU has a module called the MMU, Memory Management Unit. That is a hardware module in CPU that does the translation from the physical memory, from the virtual memory to physical memory. But the translation is through the table, the page table. So this is a typical memory map of a 32-bit Linux process. Things could be changed a little bit here and there. So at the very low memory address, we have the code, the text segment, the .text. Okay. Usually this is at a very low address, but not address 0. What is address 0? What is address 0? That's null. That's illegal address, right? So this is a little bit weird design, right? From hardware level, obviously address 0 is a valid address. Also from virtual memory address point of view, this can also be a valid address. It's just when the C programmers, the C inventors, they invented the C, they decide to say, okay, 0 is invalid. We define C as invalid. Then all the systems after that, we have to make this invalid. Okay. So this is done, for example, at the OS level. This virtual memory address is not mapped. Okay. There is no physical memory backing up this part. So that's why when you access 0, you get a segmentation fault. Yeah, but if you redesign the system, this can be valid. Why not? Yeah. Then after that, we have the .data segment. Like I said, those are for initialized variables. Okay. So in this case, we have example: static char pointer, Gonzo, God's own prototype. So this is a string, right? This is a string. This is a variable, global variable. The string, this is a constant. This is not a variable. Okay. So this global variable doesn't have the value of the string. Okay. it has the address of that string. Okay, so this global variable is initialized to the value of that. Okay, but this part itself, the string itself, is not a variable. It's a read-only data, so it can go to a read-only data section, which is not showing in this map actually. So after that, we have PSS segment. Those are for uninitialized global variables like this. Static char username, a star username. We didn't initialize that. So we didn't initialize that, which means we're initialize that to 0. So we only need to reserve that space, then memory set everything to 0, the loaders. After that, we have the heap. Okay, so this will be the topic we discuss at almost the end of the semester, how to exploit this. Higher than that, we have the libraries. So say libraries, other dynamic libraries. We can use the system called memory map, mmap, to get things loaded into this place. So we have stack goes down, the heap goes up. Okay, each thread has its own stack. Then the higher 1 GB is mapped as the kernel. So this is a 4 GB memory process. So this basically is a null pointer in C++. We just define as this. But actually the newer C++ were not defined as 0 anymore. It has a special definition for that. But we can skip this. Yeah, go ahead.
Are the random offset sizes, is that like a security thing or like why random?
There is a security thing called address space layout randomization. Because when you will say later that when you try to exploit some vulnerabilities, sometimes you need to know the exact address of that. If we randomize things, make it harder for you to know the address, then it's a security feature. But it's not that useful anymore because you find all kinds of ways for information leakage, so you can infer that to randomize the value. Yeah. So I think we can say the memory map of this. What's going on? Okay, so there is one example program. So it doesn't do anything, right? It will get a char. It wait for your input. So if you don't input, it will stay there. And then we are going to say the memory map of this program. Say maps. Process map 32. I think we need 2 terminals for this. So I use T marks here. We use 2 terminals. One terminal, we just run this program. Okay, the program is waiting for me to input. So if I input, it will exit. So if I do not input, it will stay there. Okay, then we go back to this side. We try to say the memory map of this. Let's say, great. And so this is a PID of that. So the command we're going to use is we can use pmap x pmap x. Okay. PID is 58. It's big. Okay. You guys see it? It's a little bit small. Okay. So use this command pmap. We are saying the memory map of the program. You see that's a super simple program. Okay, only waiting for you to input. So you say this is relatively lower address, right? This is the address, this is the size, and you can say This part is the code part because the permission has execution bits there, means this is a code. And you can say this is a small address, but this address is not as small as what we show in this picture, right? So this is a very old address. Now address is much higher. Yeah.
How did you make the dual window terminal?
I use tmux, so type tmux there, then control B, percentage sign. On my website, I have a cheating sheet for this. So go to the website, there is this one, tmux cheat sheet. Yeah, here. Go to the class website. Yeah. Yeah. There are other ways to do it. You don't have to use two terminals. You can run that program, then you send that background, send the program to the background, then you run another program. I think it's called BG background. Yeah. So you can say this is the code part. And it has this module name, which is the file name, the program name. Then we have the heap. So this is a little bit higher address. This is heap. Then we're going even higher. We have the libraries. So we have the libc libraries. The libc libraries also have different sections. That's why we say multiple rows of them. So some of them are code. For example, this one has X is code. Others maybe just the .data section of the libc. Could be the .read only, .bss of libc. Then after that, we have another library here. This is the loader. Then at a very higher address, we have the stack. You can see we have the stack. Yeah. Because the highest memory will be OF, right? So this is already at a very high address. So that's a memory map. Okay. System course. How about we end at 9? I sense everyone is tired, so we end at 9. But let's at least get this system course out of the way. So system course. So system course are services provided by the OS to the applications. When you develop an application, you do not necessarily directly make system calls, but your application makes a lot of system calls. Sometimes you make function calls to the C library, and the C library makes system calls. For example, if you open a file, you use a C library function open, and C library function open eventually makes a system call also called open. So that C library function is just a wrapper of that system call, which means your application can directly make system calls. You can also make a function to C library who eventually makes that system call. So in our hacking, we are going to make system calls directly because you are already hacking. If you jump to another layer, actually it's more complicated sometimes. So the system call doesn't really use the core instruction. We already talked about the core instruction. That's for function calls. That is for the username. Or if you are in the kernel level, you can also use the core instruction to call other kernel functions. But to cross the boundary from username to the kernel, you use system call instructions. The system instructions there are 2 instructions. In your newer CPU, Intel, there is an instruction called syscall directly. Then for older ones, we're going to just use an interrupt, just int interrupt. So it's a software interrupt, and the software interrupt, the code is, the number is 80. So we're going to use int 80 in hex in Linux. I remember Windows, I think the number was 21 or something, also in hex. Yeah. So Unix systems, they provide many system calls. And POSIX has a standard. They say, oh, those are the system calls your system should provide. Open read, write, close, wait, exe, fork, exit, kill, right, those system calls. I think on Windows, they don't really have fork. I think Windows doesn't have fork. Windows system call is called create process. So it's a different semantics. Yeah. Linux, BSD have more than 300 system calls. And if you took an OS class, you probably develop a system call, right? You can add your own system call. Yeah. Windows 7 has 700 system calls. Like I said, the C library, sometimes they are just wrappers of system calls. Not every C library function is a wrapper, but some of them are. For example, the change directory function in C library is just a wrapper of the underlying change directory system call. There is a tool called strace that you can trace what system calls your program is making. But for setuid programs, it doesn't work well because the strace is not a setuid program. So if it's creating another process, it will not be a setuid one. Let's say, so see if we need to go through this. I guess we don't need to do demo. We just say this one. No, let's do a demo. Maybe just here, any program. Let me first get rid of this. So we only have one terminal up. What do we want to do? So let's say you have ls, right? ls shows you the files directories in the current folder. You do a strace ls, then it shows you what system calls it makes when you type ls. So when I type ls, a new process is forked first. Then the child process will load ls, right? So that's why the very first system call you see here is exe cve bin ls, right? So we're actually, so the shell will do fork first, but that is not captured. Now after the fork, the child process will change to ls by calling the system call exe and that is captured here. After that, it will call the break system call to get where is the memory break. If you're not familiar with that concept, it's okay. It's not very important at this point. Then it will check its architecture. It will check whether this file is available. And in this case, the file is not available. Then it will try to open some files, open a cache here. Then there is a memory map here. This memory map is trying to load this file into memory. Then we are loading more memories here. Read from that open file to memory, then to memory map, allow memory map. Then eventually from here, this is actually loading the, I think this is actually loading the ALS program is actually here. Yeah. Then after that, we change the memory permissions and protect. This program, what we did, we did ls. Maybe we should do an easier program. Maybe it's okay for today. So you can say eventually the ls program will print out the files and folders in this current directory, right? And the program uses the write system call to do that. Okay. So when you print out something in C program, what do? You use printf, right? Printf is a library function. It's not a system call. Eventually, printf will use system calls like write, or there are other system calls can do that to actually print out things. So strace is the tool for you to at least know what kind of system calls the program is making. Let's skip this one. Oh, by the way, in Linux, there is a man command for you to access menus. To access menus, let's say any program here. So if you man open, usually it gives you. Oops, it's going. Okay. Man open. Here there is a number 2. Okay. The number 2 here means this is a system call. Okay. So the menu has many different sections. Section 2 is for system calls. Section 3 is for say libraries. Yeah. So in this case, it is showing you the C prototype. Okay. But this is actually a system call. Here it says open system call. Right? By showing you the C prototype, if you know how it works, then you know how to write in assembly. Let me see if we can do a man 3 here. Open. There is no 3. Man 3, man 4. No. But if let's say we do a man printf. So first of all, there is a printf command. Okay, that's why we're getting 1. 1 is command. But this is not the printf function we're looking for. So it should be 3. Okay, so you can say when we do printf 3, section 3, then we get the C library function. And this is not a system call. If we want to try to do printf section 2, we do not get anything. Okay, because section 2 is for system calls. So next, we will quickly talk about how to make system calls in assembly. We will revisit this part later. So in Linux, in 32-bit Linux, we use int 80 to make system calls. And to make a system call, you need to know the system call number. Okay, the name doesn't really matter. The name is for us to just too easy to understand. The CPU doesn't, the OS doesn't really know the name. Okay, they only know the system call number, and you need to put that system call number in register EAX. Okay. This is register. So if you want to make a fork system call, then you need to move the system call number 2 in the register EAX. The fork doesn't take any other parameters, so you don't need to set any other registers. But if you want to make an open system call, if you want to open something, you open a file, then you need to know the file name, right? File name is a string, and that file name string is the first parameter. And the first parameter goes to the register EBX, because the system call number goes to EAX. Then there are flags and also mode. So for most cases, we can set them as 0, I believe. Yeah. So file name, the string is very important. Then let's take a look at this piece of code. Then I guess we will be done after this today. Okay. Let's look at this piece of code and try to understand what it is doing. It has 10 instructions. Okay, 10 instructions. The first instruction is exclusive OR EAX and EAX. We don't really know the value in EAX, but we do an exclusive OR with the same number. What we get? We get 0, right? So basically, what we're doing this one is we are setting EAX as 0. There are other instructions, we can do this as well. We can do a move 0 to EAX, but there are reasons we don't want to do that. But we'll explain that later. Then we push EAX to the stack. Okay? EAX has a value 0. In this case, EAX actually has 4 bytes. So we're pushing 4 bytes of value 0 to the stack. Okay? Now after that, we're pushing 2 weird numbers. Okay? Can you guess what are those numbers? It's actually just ASCII string, not address in this case. So you can see. So let me see if I have slides for that. Yeah. So actually, it's this string /bin/sh. So that's our shell basically. Right? So this is a shell code. Eventually, we're going to get a shell. Yeah. So we're pushing those 2 8 bytes, which is the shell. And why we're pushing EAX the zeros at the beginning? Why did we do that? What?
Maybe a system call.
System one?
Maybe a system call.
System, all right.
Maybe a system call.
No, that's not a system call. So system call is eventually making system call is the last instruction, the int 80. Okay. So what is the end of a string? Oh,
No character.
exactly. So 0, right? So we actually only need 1 0 there, but so to make sense easier, we push 4 zeros. Yeah. So now we have a string there. /bin sh, that's a string. Now after that, we move ESP. So ESP right now points to the string, right? We move ESP to EBX. The system call we are going to make is exe save e in this case. So we're making this system call. So the first argument is what? Is the file name. Yeah. The second argument on the environment variable, we don't need those for now. Okay. So now we have the string, which is /bin/sh, the file name. Then the string's address is at ESP. We move that to EBX. Then we push EX again. So we get another 0 there. Then we push EBX. Then we are pushing that address to the stack. Because we actually needed that address on stack. Because ESP has that address, but we needed that address on stack. That's why we are pushing it again. We will revisit this later again. So then we move ESP to this. And more importantly today is understand this part. We move B in hex to AL. So what is B again? B is number 11, which is the system call number for exe save e. Then after that, we just make the system call int 80. Okay. Yeah, that's how it works in 32-bit version. 64-bit version, things will be a little bit easier. We don't need to push that onto stack. We can directly move that string to a register and push that. You notice that we have 2 slashes here. /bin //sh. Why do we have 2 slashes? Or what are 2 slashes? Anyone knows?
An escape character.
No, it's not. So in Linux, no matter how many slashes you have, it's just the 1. Okay, for the passes. Let's say, show you one example. We're trying to which program we want to use. Cat. Is there anything we can cat here? Maybe we just do echo. Okay, let me show you this. Cat. Oops. Okay, I have so many stashes, but they are actually just one. So when I do this, I still get a permission deny. I do not get a warning saying that fire doesn't exist, right? It get a permission deny. So this can come very handy when we develop share code later. Because in share code, in hacking, sometimes we need placeholders, we need paddings. And this can be a padding for passes, right? So for 64-bit, the system core numbers are changed. I don't know why they changed the numbers. In 34-bit, EXE7E was 11, 64-bit is 59. It's a little bit weird, but I don't know why. And there is a new instruction called syscall in 64-bit. Okay. You can still do int88, but you can also do syscall. I recommend you guys to read this book, Linux System Programming. It teaches you all the interfaces Linux system provides. Okay, I guess we stop right here. Okay. We still have a lot to cover for background. I feel. Yeah, maybe we need another 30 minutes for background in the next class. Yeah. But I sense everyone is a little bit tired today. So okay, see you guys next week. Any questions before we leave? Oh, good point. There is homework. Oh, because we didn't cover everything, let me see if we can do the homework. Go to the website, there is a homework link. Click this, you can download the homework. It's basically a Word document. Let's see. Yeah, you can do the homework. Everything we have done, yeah. So you can just answer in this Word document and submit to Canvas.
The deadline is like before.
Hmm?
The deadline is next week.
Yep. Okay, see you guys.
Thank you.